Hello everyone. So this is now a new chapter, entirely new topic on likelihoods. And this is now sort of where it starts getting interesting. Now that we've built up our language in terms of how to write down probabilities, and we've looked at a couple of different examples for, what are some typical probabilities we work with. At this point, we'd like to sort of turn to the topic of likelihoods. Now, if we remember, likelihoods are probabilities of the data, and we may have n data points given parameters, and we may have k of those. So this is the, more strictly speaking, the probability density of n data given k parameters. And again, the n data could be one data point, and the k parameters could also be one. So k is kind of arbitrary from 1 all the way up, and n is also kind of arbitrary. Now we need to say something about parameters, because it's not so clear, in fact, what we mean by parameters very often. So parameters is kind of tied to the notion of what it is we want to learn. So when we talked about coin flips, or when we talked about dice rolls, maybe in the case of coin flip, the parameter to learn, if we assume that each one of them was sort of IID, was sort of the Bernoulli weight of heads. And the Bernoulli weight of tails was 1 minus that. And for a dice roll, it wasn't that much more complicated. There were sort of 5 independent parameters to learn. So in those particular cases, it was clear kind of what the strategy was. The strategy was to ask, what is the probability of observing a particular sequence of data under the assumption of our model, and let's keep on tweaking, in the case of, for example, the coin flip, the probability of heads, in order to make the probability of the data that I have observed the most probable. Right? So for example, if I were to write here the probability of heads, and let's abbreviate that to pi sub h, and this was going to be our likelihood, and suppose that we had, our likelihood being W. Let's say we flipped a coin 100 times. We got heads, tails, heads, 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 and so forth, all the way up to, a mixture of heads and tails all the way up to 100, conditioned on the probability of heads. If we were to plot this versus pi h, and if we roughly had 50-50, then maybe this would kind of look like it's centered at 0.5. So in other words, the data, the sequence is the most probable given that I've assumed a pi h of 0.5. Now, it would strictly be 0 at 0 and 1. In other words, the probability of heads being 0 or 1 if I had already observed some heads or tails. So if I observe any mixture of heads and tails, then I know that pi h needs to be somewhere between 0 and 1, but cannot strictly be 0 and 1 because I've observed a little bit of both. So, next, like I said, if it's roughly 50-50, then kind of the likelihood would probably be peaked at 0.5. So it's pretty clear what we meant by parameters here. But what about sort of Brownian motion where a particle is doing something like this? So it's moving from some position Rn to some, to some final position Rn plus 1 or Rn plus, let's say, big N. What is there to learn? In other words, what is this? It depends. And this will sort of lead us to a discussion of complete and incomplete likelihoods. It also immediately leads to a discussion of sort of latent variables versus non-latent variables. Maybe in my theta are included the positions that I would like to learn. Maybe the positions are uncertain. Maybe I have noise in my experiment. So I'm not exactly observing the positions along this trajectory, but rather I'm observing some kind of deviated, corrupted version of them. So I'm observing this when the actual trajectory may be a little bit different. It may be something like this. So maybe something that I'd like to learn would be the positions of all the particles. And realistically speaking, since these are realized positions, I suppose I can call them small r. Maybe I might want to learn the positions of all particle and on top of it the diffusion coefficient. I don't know. Or maybe if the experimental noise is very small and I can more or less pinpoint the positions to where, where it's obvious and I don't need to learn them, then maybe all there is to learn is one thing, and there's only a theta 1, and that theta 1 is the diffusion coefficient. So in the case that I have to learn positions and diffusion, maybe I would call this to k being n plus 1, for example. So there's different questions we can ask. Now, I mentioned sort of the word latent variable. So latent variables, whoops, let me write this a little bit more neatly. Latent variables those are really parameters, in a way, that we do not wish to estimate. So there are parameters we care about, and there are other parameters we don't care about. So, for example, it could be the case that there's a lot of experimental noise and I can't learn the positions very well, but actually I don't care about those. So I would call those latent variables. I would not want to learn about them. And maybe the thing that I would really want to learn about is a diffusion coefficient. So that at that point I would call a parameter. So as another example, suppose you have a particle that's sort of diffusing in a harmonic well. So the particle starts off somewhere and it's kind of trapped in this well and kind of, fluctuates along in this well. So, for those in physics, this could be sort of a random, a harmonic oscillator with some kind of random motion. So I may want to learn kind of a diffusion coefficient telling me about the motion in the well. I may also want to learn sort of the stiffness of the trap of the well, the force constant of the particle, but I may not actually care about its actual position. So if I don't care about the position, I would call that a latent variable. And these I would call these sort of the parameters that I want to learn. This is just a slightly more sophisticated example of the Brownian motion we saw earlier. In Brownian motion, I would kind of randomly go anywhere I like. Here you're sort of confined to some kind of, well. So when we do maximum likelihood, and what do I mean by maximum likelihood? We maximize our likelihood, which is, again, the probability of the data, typically given the parameters that we want to estimate. So these are parameters we want to estimate. We obtain estimators of our parameters. These are called estimators. Now, what about those parameters that are latent variables? We'll treat those later because in some sense they're going to be complicated. They're going to appear in the likelihood and yet we don't care about them and we don't even know what their values are. So those are going to have to be sort of treated on a special basis, and it's a slightly more complicated topic that we'll turn to in this chapter. But for now, we will assume that there are no latent variables, and every parameter that we've listed here, we'd like to estimate. So all of this looks great, and this is one way of estimating these parameters, but there are some questions. What if the likelihood is not single peaked? In other words, it's not a unimodal distribution. So that not only introduces computational problems because, when we start discussing kind of algorithms for obtaining sort of the maximum of a likelihood, that's the possibility that the likelihood may be multi-peaked in many dimensions is going to create a big mess. But there's something even more sort of conceptually concerning about this first point. And if my likelihood kind of has two peaks, something like this, so I'm plotting the likelihood versus theta, and it has two peaks, then which of the values of theta should I select as my estimator? Right, it's not so clear. Now, what if one of the peaks is just 1% lower than the other? Should I commit 100% to saying that the value of theta that maximizes likelihood is, for example, this theta 2, as opposed to this, well, let's call it theta 1 star versus theta 1 double star? It's not so clear. What about the uncertainty in theta? What about the fact that I may be uncertain about theta, right? So if I flip a coin once, I'm going to get a probability of heads. Something will maximize my likelihood. If I flip it twice, presumably my estimator is going to change. So somewhere in the estimator or somewhere in the likelihood should be contained the information about my certainty as to the value of my estimator. So that's not super apparent from this here. Now you could argue that if the likelihood maybe has a single peak, so again, if I were to look at the likelihood versus some theta 1, I only have one parameter, you may be able to argue that, well, maybe the breadth or the variance of the likelihood around its maximum tells me something about the uncertainty. Well, typically speaking, the likelihoods we look at are not one-dimensional. And more often than not, they are multi-peaked. So, the spread around what parameter and what dimension are we talking about here? So, sometimes it isn't, these points aren't so clear. So, simply maximizing the likelihood is something called or yields what's sometimes called a frequentist, that's estimate. Frequentist estimate. So you're sort of counting the frequencies of events, kind of coin flips or whatever, and then using those to sort of obtain an estimate for what your theta is. By the time we get to chapter 4, we will be discussing maybe a slightly different and more general way of obtaining estimates, and those are Bayesian estimates for, and we're going to be focusing on the distribution of our parameters given the W 1 to n. And this, looking at this object, which we'll turn to and we'll discuss in detail by the time we get to chapter 4, this object here is called a posterior, and I need a likelihood in order to construct this object. So this here should really be just a straight line, a conditional. I'm going to need a likelihood in order to construct this object. We're not going to say much about it here except for the fact that if I can construct what are reasonable probabilities over what the values for thetas could be given the data that I have observed, that seems to address the questions that we posed or the concerns that we listed in the last slide. So let's go ahead and talk about how we estimate, again, ignoring latent variables, how we go about estimating parameters such as diffusion coefficients from data. So this will be a very simple example. And it will use sort of, again, no latent variables, just the straightforward application of the principle of maximum likelihood. So just to lay it out, the principle of maximum says, write down the likelihood of your data or your observations, write W1 to 2. And secondly, find values for the theta 1 to k that maximize the likelihood. Okay, so let's look at this sort of in the context of a simple kind of Brownian example. So this will be a maximum likelihood estimation of my D, which is my diffusion coefficient. Okay, so let's assume that we have Brownian motion. So let's assume that we have Brownian motion. Then we have a P of R of n conditioned on Rn minus 1. I know I've written it out as Rn plus 1 conditioned on Rn, but that's the same thing. And I should be a little bit careful. And D, the diffusion coefficient. So my future position depends on my previous position and my diffusion coefficient. And if I normalize my Gaussian properly, I have here a 4 pi d tau. And I multiply by some, well, the Gaussian, so Rn minus 1 squared divided by 4d tau. And you can say, well, where does the factor 4 come from? That's in the definition of the diffusion coefficient. So the diffusion coefficient is defined in such a way that you have this additional parameter staying out here. We sort of discussed the details of that in the advanced sections of Chapter 2. Now, we can ask ourselves, what is the probability of observing an entire sequence given a diffusion coefficient? Well, that's kind of interesting. If my diffusion is a Markov process, which it obviously is, right, because my future position depends only on where I started from, not sort of 3 steps behind, then in principle I can rewrite this as the probability of my initial position multiplied by the probability of my first position given my initial position and diffusion coefficient multiplied by, all the way out, R2 given R1 and D, and Rn given Rn minus 1 and D. So if I were to take all this and simply write it out as sort of a neat product, I would have P of R naught. And then let's just erase a little bit of this. Product from n is equal to 2 all the way up to n of P of Rn conditioned on Rn minus 1 and D. That's my likelihood. This is R small n. I know how to write this down, this expression here, because I know exactly how to write down those. So my P of R1 to n, my likelihood, conditioned on D, is P of R naught multiplied by, actually I think it should have been R1 in the last slide. So it should have been R1 product n is equal to 2 to n P of Rn conditioned on Rn minus 1 and D. So it starts from 1. It doesn't start from 0. Not a big deal. Anyways, so let's go ahead and write this out explicitly. I know what the form of this is for Brownian motion. It's the, individually these are Gaussians. So this is going to be 1 over 4 pi d tau, all raised to the n minus 1 divided by 2. That's because I have a square root as a normalization. And then I have e, and I have to be a little bit careful, sum n from 1 to big N, negative sign, Rn minus 1 squared divided by 4d tau. You're going to say, where does the sum come from? Well, remember, I'm taking the product of very many exponentials. So if I have e to the x times e to the y, that's equal to e to the x plus y. Similarly, I have the product of very many Gaussians, so I can rewrite that as e raised to the sum of each one of the arguments. Good. And now my goal, I know what these positions are. Those are my data. I plug all those numbers in. And finally, my goal is to maximize my likelihood with respect to the only thing I care to learn, and that's my diffusion coefficient. Now, why am I using partial derivatives? Don't need to. I guess most of the time the likelihoods will be, multidimensional. In this particular case, there's only one parameter, a theta1, that we're trying to learn. So we're going to take a derivative of that. It's more convenient oftentimes, both computationally and analytically, to consider taking derivatives of the log of the likelihood. Why is that? Well, computationally, the likelihood itself is going to be an extremely small number. It's going to be the product, typically, of very many small things. And so that might cause numerical underflow. So in particular, then, what we'd like to do to avoid this numerical underflow is to consider the derivative, I'm going to use partial again, of log, under the assumption that whenever I write log, I mean natural log, which is more convenient, of this, and I set that equal to 0. Now, because the log of a function is monotonic with the function itself, in other words, they have maxima at the same location, then the maximum of the log of the likelihood will be exactly the same as the maximum of the likelihood originally itself. So that actually makes sense. So let's proceed forward by then saying, plugging what we had derived earlier for P of R1 to n conditioned on D with respect to the diffusion coefficient to see what we find. So the log of the likelihood is n minus 1 divided by t log of 4 pi d tau. That's the log of the normalizations minus sum n from 1 to, or 2, sorry, to big N, Rn minus 1 squared divided by 4 d tau plus the log of the initial condition, close bracket, and I have to set this whole thing equal to 0. Well, something's interesting going to happen, or something interesting is going to happen. If I take a derivative of the diffusion coefficient, if I take a derivative with respect to the diffusion coefficient of the initial condition, that gives me 0, because the initial condition does not depend on my diffusion coefficient. I start off at some initial condition, and then where I go next depends on my diffusion coefficient. So the probability of observing a particular trajectory is P of R1, where I started from, which does not depend on my diffusion coefficient, multiplied by sort of this Markovian transition probability density, which I said was, in this particular case, took the form of a Gaussian for Brownian motion. So if I take the derivative with respect to the diffusion coefficient of the first term and the second term, that I can do. And if I take the derivative of log d, I know that that becomes sort of 1 over d. And if I take the derivative of this 1 over d, I know that this becomes, negative 1 over d squared. So if we trust that I know how to take these derivatives, and this is n minus 1 divided by 2d, let's call it hat, so let's just write it a bit neatly, n minus 1 divided by 2d hat, plus sum from n is equal to 2 to n. The plus, by the way, came from the fact that I was taking a derivative of 1 over d, which brought out a minus sign. Rn minus 1 squared divided by 4d squared tau equals 0. So obviously one possible solution to this equation is that d is infinity. Okay, but that's sort of the trivial solution. There's the other solution where d is not infinity, where at this point I can now solve. And the other solution, if I write it correctly, is 1 over 2 n minus 1 tau sum from n is equal to 2 to big N Rn minus 1 squared. What did I do here? Or how do I interpret this? My diffusion coefficient estimate is basically the sum of the square differences in the positions divided by the time interval and the number of data points. In some sense, the way I can interpret this is that this is sort of the area that I cover, and I've summed over n Right, so it's kind of an average area that I cover divided by the amount of time that it takes me to cover that area. Intuitively, that's sort of how I interpret my diffusion coefficient. So how much area did I cover in some amount of time tau? So if I had started here, maybe in some time tau I end up here, then I end up here, or maybe some other time I end up here. But on average, the area that I cover is roughly this region here. That tells me something about the diffusion coefficient. Or similarly, if I specify the diffusion coefficient, that kind of tells me the area spanned per unit time. So right now, from the area spanned per unit time, I get an estimate for my diffusion coefficient. Let's ask something a little bit more complicated now. Suppose that I observe my particle at various different points in time. And from this, I'd like to estimate a diffusion coefficient. So I'm going to do the same thing. I'm going to write down my likelihood. My likelihood is going to be the probability of R 1, 2, 3, 4, 5, 6. Yep, P of R 1 to 6 given my diffusion coefficient. And if I maximize my likelihood with respect to D, then I'm going to get some estimator for my diffusion coefficient from this trajectory. Great. Suppose that I ignored measurement error. In other words, this is what I measured. These points here are what came out of my apparatus. But in reality, the apparatus is not perfect, and it reports something which is pretty close to the correct answer, or can be completely off from the correct answer. So suppose that the correct answer is the star. So let me draw a line. What we can see here is that there seems to be a lot of noise. This point, for example, was not reported at the correct value at all, if my instrument had some kind of noise, but was reported kind of pretty far away. This one happened to be close, but this one was also pretty far away. What if I ignore noise? What if I say that my positions are the true positions? What happens to my estimate for the diffusion coefficient? That's an interesting question. I'm going to ignore the fact that there are true positions, and I'm just simply going to assume that the positions that I measure. I'm going to ignore noise, and I'm simply going to assume that the positions that I measure are correct. What's going to happen? Well, I will also estimate a diffusion coefficient, but that diffusion coefficient will be a lot larger than the true diffusion coefficient. Why? Because that diffusion coefficient will be sort of integrating all of the effects of noise that I've ignored. Now, in the extreme case, suppose the particle is doing this. But suppose that because of noise, you're measuring positions here, 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 and there. Of course, if you assume that the particle is doing this instead of doing this, the diffusion coefficient, the apparent diffusion coefficient, will be much, much greater than the actual diffusion coefficient, because you're ignoring noise. So if your apparatus has noise, all of a sudden we need to start worrying about latent variables, because at this point we cannot simply assume that what we see is correct. And we may not actually care about learning those positions. We may care about learning diffusion coefficients, irrespective of what the underlying position was, given what we know, for example, about the instrumental noise. It's a more complicated problem, but we're sort of building towards it. But at the very least right now, what you can appreciate is that maximum likelihood is a tool, well, at least for the simple example that works, gives us a result that's sort of intuitive, that diffusion is sort of an area span per time, but that if there's instrumental noise, then we need to improve on the maximum likelihood. We need to sort of expand what we described here. We can treat experimental noise within the likelihood paradigm, and it's going to lead to sort of refined estimates for our diffusion coefficients. So there's a lot more to say about likelihoods, and we'll talk about it next time. Thank you.